A battery that outlives you, your children, and possibly your grandchildren. No charging, no maintenance, just continuous power for a century. China just made it real, and the world is not ready for what comes next. The device is called the BV100, developed by Beijing-based Betavolt, and it does something that should not be possible with current battery technology. It generates continuous electricity for up to 50 years, using the slow radioactive decay of nickel-63, with researchers already working on a carbon-14 variant that pushes that lifespan toward 100 years. No charging cycle, no replacement, no degradation in the way every chemical battery you have ever owned has degraded. Just steady, quiet, uninterrupted power produced at the atomic level. And it represents the opening move in what may become the most consequential shift in energy technology since the lithium-ion battery changed the world 4 decades ago. To understand why this matters, you first have to understand what makes every battery you currently own fundamentally limited. Chemical batteries store energy and release it through electrochemical reactions that physically degrade the materials inside with every cycle. Every charge and discharge wears the battery down. After a few hundred or a few thousand cycles, capacity drops, performance fades, and eventually the battery dies entirely. This is not a manufacturing flaw or an engineering oversight. It is an unavoidable consequence of the chemistry involved, and it is the reason you charge your phone every night, replace your laptop battery every few years, and watch electric vehicle range estimates slowly decline over time. Nuclear batteries work on an entirely different principle. Rather than storing energy, they generate it continuously from the natural decay of radioactive isotopes. As those isotopes shed electrons during the decay process, advanced semiconductor materials capture those electrons and convert them directly into usable electric current. The energy source does not deplete in any meaningful human time frame. It simply keeps decaying slowly, predictably, and continuously, producing power whether or not anything is drawing from it, in temperatures that would destroy conventional batteries, in environments where recharging is impossible, for spans of time that make the word battery feel almost inadequate. The BV100 produces approximately 100 microwatts at 3 volts, modest by the standards of consumer electronics, but more than sufficient for the enormous category of devices that do not need high power but absolutely cannot afford to lose it. Medical sensors, aerospace instruments, deep-sea monitoring equipment, IoT nodes, and implantable medical devices all operate within this power range, and all of them currently face the same recurring problem. Batteries die, replacements require intervention, and in many of these applications, intervention is expensive, dangerous, or simply impossible. A pacemaker today requires surgery every 10 to 15 years to replace its battery. A nuclear battery lasting 50 years or more eliminates that surgery for the life of most patients. A sensor buried under Arctic ice or on the floor of the deep ocean, monitoring climate data that scientists need to understand the trajectory of global warming, currently dies after a few years and takes irreplaceable data collection with it. A nuclear battery changes the economics and feasibility of that monitoring entirely. Betavolt has already stated plans for a 1-watt version in the near future, which would push the technology into an entirely new range of applications and begin closing the gap between what nuclear batteries can currently power and what the broader market demands. The safety profile of this technology is one of the most important and most misunderstood aspects of the story. The word nuclear triggers associations with reactors, meltdowns, and radiation, and none of those associations apply here. There is no chain reaction inside a nuclear battery. There is no intense heat, no coolant required, no containment vessel. The isotope in the BV100 nickel-63 decays into stable copper over time, a process that is entirely contained within the sealed unit and produces zero emissions into the surrounding environment. BetaVolt reports that the battery can operate safely across temperatures ranging from -60 to 120 degrees Celsius, will not catch fire, and will not explode even if punctured. For industries where chemical battery failure means a fire on an aircraft, a malfunction inside a human body, or a power loss in a system with no backup, this combination of longevity and stability is not a luxury. It is a fundamental requirement that current technology cannot reliably meet. China's ambitions in this space extend well beyond the BV100. Researchers at Northwest Normal University and partner institutions are developing nuclear batteries based on carbon-14, an isotope with a half-life of 5,730 years. A battery built on carbon-14 does not face meaningful decay within any human time frame. It will still be producing power a century from now at nearly the same rate it produces power today. Laboratory tests of these carbon-14 designs have already powered LED lights and Bluetooth chips for months of continuous operation without performance loss. A more advanced device, referred to by researchers as Zhong-1, has demonstrated the ability to function across extreme temperature ranges, while sustaining electronic components in uninterrupted operation. The research teams claim these batteries achieve higher energy density than some conventional batteries while maintaining the ultra-long lifespan that defines the category. What is being built in Chinese laboratories right now is not an incremental improvement on existing battery technology. It is a parallel technology with a completely different relationship to time, and the implications of that difference compound the further out you project them. Consider what a 100-year power source means for space exploration. Satellites orbiting Earth require power systems that degrade as little as possible over operational lifetimes that can stretch years or decades. Deep space probes cannot be serviced by human crews and depend entirely on the reliability of their onboard power for every instrument, every transmission, every course correction across billions of kilometers of empty space. The nuclear batteries currently used in deep space missions, including radioisotope thermoelectric generators, are large, expensive, and dependent on plutonium-238, a material that is extremely difficult to produce. Beta-voltaic nuclear batteries, using more accessible isotopes, scaled to higher power outputs, could eventually offer an alternative that is smaller, lighter, and producible at a scale that makes ambitious space programs more economically viable. On Earth, the transformation of environmental monitoring alone would be significant. Climate scientists, oceanographers, seismologists, and disaster prediction systems all depend on sensor networks that are currently constrained by how long their batteries last and how accessible the deployment sites are for maintenance. A sensor that runs for 50 years without intervention, installed in a volcano, on a glacier, at the bottom of a trench, or along a fault line, generates a quality and continuity of data that simply does not exist today. When the power source outlasts the researchers who deployed it, the science it enables changes in kind, not just in degree. The limitations of the current technology are real and worth stating clearly. 100 microwatts does not power a smartphone. It does not power an electric vehicle, a household appliance, or any of the high-drain devices that define modern consumer energy consumption. The physics of beta decay from nickel-63 and carbon-14 produce continuous but inherently low-level energy, and no engineering innovation changes the fundamental output of a decaying isotope. The path from where this technology is today to a world where nuclear batteries replace the lithium-ion cells in consumer electronics is long. And it may never be completed for applications that require high instantaneous power. What the technology does right now, and does better than anything else available, is provide reliable, maintenance-free, long-duration power for low-energy applications. And that category is enormous, growing, and currently underserved in ways that cost industries billions of dollars and cost patients real medical risk every year. China's investment in this space is deliberate and strategic. BetaVault has moved from research to pilot production of the BV100, and the company has stated publicly that mass market availability is approaching. Academic institutions are publishing research that advances the carbon-14 designs toward commercial viability. The manufacturing ecosystems that China has built around battery technology over the past 2 decades, the supply chains, the production facilities, the engineering talent, are now being turned toward a category of power source that the rest of the world is still largely treating as a long-term research question. That gap between treating something as a future possibility and treating it as a near-term product is where industrial advantages are built, and China is on the product side of that gap right now. A battery that outlives everything it powers, that needs no charging infrastructure, no replacement logistics, no maintenance schedule, built at scale, deployed across medical devices and space systems and environmental sensors, and the billions of IoT nodes that will define the next decade of connected technology, is not a curiosity. It is a platform. And the country that commercializes it first will have built something that compounds in strategic value for decades. Subscribe to Business Hook for more stories about the shifts in technology and economics that are rewriting the rules before most people realize the game has changed.